Now to the last part of this presentation, when it's related to 6D pose estimation. So let's say you already have a model of the object. You have shape 3D model, 3D CAD model that is given to you, or maybe this model has been completed by the methods that we presented before for shape completion. Now you have completely new scene where you have objects that you know they are models, and you want to know where these objects inside the scene and where they placed physically, like what's their XYZ position and what are their 3 degrees of rotation. And so basically the first question can be answered by using standard detection methods like convolutional neural networks, and second one is called pose estimation, and consists in finding transformation from the full 3D model that we have into the point cloud that we are observing. And this is made by 3 components. The first one is just 3D translation, and second one is rotation, 3D rotation. This is called a 6D pose estimation. So we can use then convolutional network to first detect where the objects are, and the big problem with CNNs is that they are data hungry. So the first solution is to train them in synthetic image in simulation. And one advantage is that if you train them in simulation, this is going to be free. You don't need to label the objects manually. You can just automatically compute from rendering. You can know where the objects are, and you know what are their the label of each pixels. And then you want to transfer this into real scenes where you can detect the objects. So you generate objects in physics simulation, and this is also important because you want to have scenes that are physically they make sense. You don't want to have objects flying in space. You want objects that are stable, and you don't have to have objects that are colliding with each other. So you want to generate scenes that are physically closer to the real world, basically. And one problem that you will run into is this gap between simulation and reality in terms of the realism of the image. So if you just train neural network in simulation, it's not going to transfer easily to the real world. So you need to do this typical adversarial training with unlabeled real data. So we want to combine labeled synthetic data with unlabeled data from real image. And then you want to train the neural network such that the output would be similar regardless if the image comes from simulation or from the real image. And you do this by adding domain classifier that tries to learn if the input is coming from simulation or from reality. And this is trained in adversarial way with respect to these 2 networks where the first one is predicting the label of each pixel and the other one is predicting the boundary in the image. So let's say you do that, and then you get this neural network, and then you want to use it for pose estimation. So a typical approach would be to do segmentation and then do 3D model alignment, and then from there you can conclude the 6D pose of the object. But if you do that, you're going to run into a lot of problems. We tried that because segmentation is far from being perfect. Sometimes you under segment, sometimes you over segment the objects, and slightest errors they can lead into a big problem when it comes to 6D pose estimation. So the solution that we proposed is, instead of using this hard segmentation, we're going to use soft segmentation, where the output there is not a rigid segmentation, but it's a distribution on all the possible labels for each pixel. And this will give us much more flexibility when we will try to fit models. So if you have this, instead of having finite segment, you can have for each pixel you can have distribution of all the objects that it could belong to, and that can help us having more flexible model fitting. And then this is just very quick summary of the method. So basically you start by, you have an object of interest, let's say it's an expo box, and then you see this scene, and then you start by taking the output that you get from the neural network that gives you for each pixel distribution on all the labels, possible categories or possible objects that it belongs to. You get 4 points, and then you sample 4 points through this distribution. And then you look into your model of the object of interest that you are looking for, like an expo box, which is not the correct one here. We are sampling points from Kleenex. So you can look into that model, and from that model you want to find 4 points or base of 4 points that are congruent to the 4 points that you sampled from the point cloud. And you want to find a mapping between these bases of 4 points. and you end up with a large set of bases of 4 points, because there are many parts of the object that match to the same part that you sampled from it, these 4 points. And for each base that you sample from the CAD model, you want to compute the corresponding transformation. So you end up with a lot of possible poses, a lot of possible transformation. But what you'll be doing is you can be evaluating how good each one of them. So you can compute each one of them by using least squares, and then evaluate how good the alignment is. At the end, you will return the one that is most likely to give you the best alignment, the one that gives you the least error. And this will be your answer. So this is demonstration of this algorithm on real objects, real scenes. So on the left side, we have a point cloud, and you can see in real time, so this is showing the algorithm working in real time, how the algorithm is fitting models into that point cloud. So it's detecting where they are, and it's also computing transformation and translation, and fitting CAD models into the scene. And these models then, once you feed them into the scene, once you know their poses, you can then plan in simulation to grasp them. You can do all sorts of things with this method. On the bottom, what we have is a heat map that describes the location of each pixel of each object in the scene or in the image. So it worked very well. We compared this algorithm to state-of-the-art pose estimation methods such as pose-CNN, Super 4 PCS, which has also the idea of using 4 bases, but with deterministic segmentation, and a lot of other methods. And this method is the state of the art in solving this problem. And that paper was published BMVC 2018. So one thing we noticed with the output that we get from this method is that the objects are not necessarily physically correct. They are not physically consistent. So basically you may end up with boxes that are basically unstable, or the object is going to fall, or maybe you have objects that are colliding with each other. They are going inside each other. So you need to have scene level reasoning. You cannot reason about each object separately, because what makes a good pose for an object maybe is not correct pose if you look into an object next to it. So I want to enforce that, and this is the results that you get if you add this physical reasoning. You're going to get much more accurate interpretations of scenes, and I will explain how to do this. So basically, we need to the idea here is to use Monte-Carlo tree search, because this is combinatorial optimization problem where you want to optimize the pose of each individual object in the scene. So you can start at the top, and then you select the object that is less dependent on the rest. Maybe it could be the bottom object. And then you want to search through all possible poses that you can assign to this object. And then you pick one of them, you assign it to the object, and then you go to the next level where you'll be inserting a second object that you are seeing in scene. And then for that second object, you might also want to consider all possible poses. And then you select one of them, and then you go on and on and on. So you assign at each level of this tree, you will be assigning a pose to an object. You will end up with, at the end, full assignments of poses into objects at the end of each branch. And then you want to score it based on how much it matches with reality. And at each level, you want to, since there are multiple poses that you can assign to each object, you want to trade off exploitation with exploration. And we do this by using this upper confidence bound, and UCB, which is a very popular method for Monte-Carlo tree research, where you want to favor branches or options that you haven't explored a lot before. At the same time, you want also to explore branches that look more likely to succeed into giving you more realistic scene. So this is the same algorithm that's used, for example, for AlphaGo, for people who are not familiar with Monte-Carlo tree research. And we are using it here for assigning poses to different objects, and scales well with the number of objects. At the end, you will be choosing, of course, the branch that gives you the highest score. So this is just an extension of that work with additional improvements, where we, instead of using the Monte-Carlo tree search, we used integer linear programming, where we have these variables that we denote by yij. They are kind of switch variables or assignment variables, where yij equals 1 means that a certain pose has been assigned to object I. Okay, a specific pose is assigned to object I if yij is 1, is equal to 1. And that it could be 0, that means that we didn't make that choice. So this is kind of sub-sum problem, where you want to You have multiple choices or assignments, and then you want to choose the optimal assignment that minimizes the total sum of losses. And the loss here is defined by function f, or actually it's the quality in this case because we are maximizing. So the quality is defined by function f. For each pose, for each object, we have a measure of quality. And actually we learned that quality function from data, and we found that actually we can, by combining multiple quality functions, you can combine them to learn a very accurate, more informative quality function. And we have constraints, of course, about the collisions, such that we don't want to choose two poses that are for two objects that are colliding with each other, for example, or that are not physically consistent. So this is the result. On the left side, we have an image where we have multiple instances of the same category of objects, and this is very confusing for pose estimation because the boundaries are not very easy to see. Everything looks just like a red or white. And on the right side is the output that we are getting with this algorithm. This was published at Coral last year, and there are more quantitative results and comparisons to related works. So the last thing I want to talk about regarding this subject is this lifelong self-supervised learning property or idea. And the idea there is that you train in, let's say you collect data, you train the detector, you have a pose estimator, you have a system that works well, but then you want to enhance it by adding data that the robot can collect by itself. So the robot can put objects in front of it. It knows maybe these objects, it can detect them, but not very well, maybe at the beginning, and then it can start creating scenes that are more challenging and take image and then label them, because we already have somehow accurate detector and pose estimator that we can use to generate labels and to generate poses for these images. So basically the robot will be just manipulating the objects and creating more challenging scenes that it knows in advance what are their locations, take their image, and then improve the detector, the convolutional neural network, based on this new data. We can also take images from different angles, and then we can transfer more information from one angle to another angle, because we do know the rotation of the robotic arm as we are moving it in space. So we do know, if we take an image from different angle, we do know which objects are there, even if they are occluded in the new angle. So basically you can generate a lot of new images like this that you can label without any human intervention. And actually I wasn't sure if this, you can also actually, the robot can also manipulate objects by moving them, pick an object and put it in different location, and then take new image from that location where there is more clutter, and then label it automatically because we know which object it picked. So basically the robot can create its own examples to improve the convolutional neural network. I wasn't very sure that this is going to work. I was surprised actually that it worked, because it wasn't trivial that you can improve over, you can learn from examples that are labeled by something that you already learned. So it seemed like kind of not adding any information. But actually, if we use just the convolutional network trained with the data that we had before offline, we get 70% accuracy. And then if we add these examples that are collected by the robot itself and labeled by the same convolutional network that was trained offline, its performance jumped to 82%. This was also the case for 6D pose estimation. So we also had some applications of this work on computer vision where that I don't have a lot of time to talk about. So one of them is bean packing, that was in collaboration with the industry partner, where we take objects on one bean and then we insert them carefully on the other bean by computing the position, orientation, by detecting the objects and planning how to place them, and doing even like rotating objects like you can see here. And we also extend this work into non-prehensile rearrangement of objects, where we push these objects very quickly to make a certain pattern. And these are all applications and extensions of that work on computer vision. So let me conclude here with the big picture. So the big picture, as I see it, is the following. Let me just put my camera somewhere here. All right. So what we have here is is combination of the ideas that I presented before and some future work that I want to do. And I think that that gives us the entire view of this area. So what we have as an input a new scene with new objects that we haven't seen before. We can insert this into a module that does policy search and tries to figure out what to do with that, with what we are seeing here. And then at the same time, we need to insert them into a model-free reinforcement learning that was trained to deal with this kind of situations. So if you have like a new scene, it can generalize from scenes that it has seen before and learned what would be the optimal policy for that. But as we know, reinforcement learning doesn't generalize really well to completely new scenes with new objects. So the policy that we would be getting from there, I would consider it more as an initial policy to use in this policy search. So we cannot execute it directly. And I think the value function of the policy or Q value function is going to be used as a heuristic if you use, for example, a Monte Carlo tree search in your policy search. If you want to do planning, like tree kind of planning, like thing that has been done in AlphaGo, then you will be using the value that you will learn from model-free RL. You can be using it as a heuristic to drive and to speed up the policy search. So it serves more as computational speed up. You get from the policy search, you're going to get some policy pi. You're going to put it into a controller that gives you a sequence of actions. And then that sequence of actions, you can give it to both the simulator of the robot and the objects and to the physical robot and objects. You get two different trajectories, 2 and 2 star. You're going to compare them and take that difference and put it into a model identification module, which is either for shape completion or identifying physical properties, mechanical properties of objects, like in the methods that we presented before. It could be differentiable physics engine, or it could be Bayesian black box optimization. And then this module will return the physical parameters theta, and those parameters, they can go into the simulator again, so they will be improvement of the model that we have about the object and the robot in simulator, and next time we're going to get more accurate trajectories and predictions from simulator. Now the simulator is useful for policy search. So because policy search is going and planning, for example, is going to be done on the simulator, so we need to have very accurate simulator. All right, and you can also train this model-free RL. You can also train it directly on simulator, such that because it requires a lot of experience, so you can do it for free on simulator if your simulator has been tuned on the real data. All right, then the last component is the initial model for model identification. So this model identification, in the way presented so far, starts from scratch and or assumes it knows nothing about the objects. But in reality, there are a lot of tools in deep learning that can give us an idea of the either the pose of the pose of the objects if we're looking into pose estimation, or the shape of the objects if we're looking into shape completion. There are deep learning methods that can complete shape, or the mass of the object or mass distribution of the objects from image, or the material properties, which would indicate the mass and the friction also. So all these can be also obtained from deep neural networks, just given the image of the new scene with new objects. But the way I consider this is that the output that I'm going to get from that deep neural network is not going to be something I'm going to trust 100%. I want to use it as an initial seed for this model identification that is more computational expensive, but it's more grounded into the reality, basically, of what I'm seeing right now. So model identification is more grounded into the instance that I'm dealing with right now, as opposed to these prior networks that are trained offline with a lot of objects and are very generic, basically. So I think this could be a nice combination of all different tools in planning, policy search, simulation, model identification, and using DeepRL as for giving initial models or initial policies for robotic manipulation. So future works, first thing is that I'm looking into is how to consider multi-scale differentiable physics engines. The idea of looking into an object as 1,000 of small pieces and you want to identify the properties of each piece is a little bit extreme. So we want to look into objects as a combination of small objects, but they have varying resolutions. So some objects are very homogeneous, others are highly heterogeneous. So we don't want to treat all the objects the same way. That's one idea, and they think it makes sense. The second thing is the combining analytical models with statistical models, and they think that relates to this idea here of model identification with using neural networks as priors, or deep neural networks as providing prior models. And then the third point is using differentiable physics engines with differentiable 3D renderers. So actually there is a lot of recent work on renderers that are differentiable, where you can calculate the derivative of the image with respect to the pose of the objects, and they are very time efficient. So if you integrate that with the differentiable physics, that gives you actually derivative of the 6D pose with respect to the mechanical properties, I think you can end up with an architecture that is end-to-end, where on one hand you have an image, on the other hand you have physical parameters like friction, mass, and then you can compute how little change in the mass or friction or forces or velocities would affect the change in what you are seeing. And this could be really nice framework for planning and decision making and manipulating objects. The last point is the relation with intuitive physics models. So Joshua Tannenbaum, from MIT, has been working on this idea of intuitive physics. And the idea there is that, humans, they don't have, in general, they don't know, laws of physics precisely, and they can work well in the real world. So they do know that objects fall. We do know that if you push something, it can also move forward, etc., without having to know exactly the precise laws of Newton. So this is a little bit puzzling. So how can we make robots able to manipulate and use tools without having to know all the details of physical properties? And what's the relation between these two research areas? This is something I want to explore more. So finally, I would like to thank my 3 PhD students who did all the heavy lifting for this work that I presented: Chankyu Song, Chaitanya Mitash, and Liam Schramm, and my postdoc Avishai Sentov, who just took an assistant professor position recently, and then my collaborator Kostas Bakris from Rutgers University. And thank you very much for paying attention.